Okay. So I was told to say something about measure rigidity. So I have three lectures. So I can't do a whole lot in 3 lectures, but I'll try to say something. So here, there's sort of 2 flavors that I think of. So measure rigidity. So in some sense, various flavors are, you have some group G acting on some space. And in the flavor I'll talk about mostly is you have H is a subgroup of G. Mu is H invariant. And all my measures, well, not all my measures, but all my undecorated measures will be Borel probability measures on some reasonable topological space. So if mu is an H measure plus, and then you have to decide what sort of flavor of world you're looking in, but some sort of dynamical or something, some sort of assumptions implies that mu is actually G invariant. And this is the flavor that I'll focus on. But there's some other kinds of flavors which sort of sit in the same sort of picture, which is that maybe nu is a measure on G, and maybe you're looking at mu, and sorry that this notation is exactly backwards from what Nikolai did. So mu would be a new stationary measure. And when does this imply that mu is actually a G measure, is G invariant? And this kind of flavor is extra invariance. So here you're only assuming H invariant, but somehow you get some G invariance from something. And of course, they're played in places where you have stationary measures that are not invariant. So of course here you also need some assumptions. And this often goes under the name of stiffness. So this is just some sort of cartoons about flavors of things, and this is the setting I'll focus on. Okay, so let me be super concrete. And of course, so there are experts in the audience, so I'm ignoring you, but the non-experts, please interrupt me with questions. And apologies to the experts that have heard me babble about these things before. Okay, so here's a very concrete world to work in. X is the circle, which I think of it additively, so R mod Z. And I'm going to take a single map of F as the starting point, so F from X to X. So F of X is 3 times X mod 1. This is the tripling map. And if we just consider a single map, there's sort of there's a whole zoo of closed invariant sets, and closed invariant are invariant ergodic probability measures. So here's sort of a fact. For every, what's a good number? Gamma, 0 less than or equal to gamma, less than or equal to 1. There exists 1. There exists a closed F invariant set. Let's call it lambda inside of S1. And 2, there exists an ergodic Borel probability measure. I'm going to stop writing Borel and probability measure mu on S1. Ergodic Borel, let's say, make sure that it's F invariant with the Hausdorff dimension of lambda equals gamma. So you can find lots and lots of fractal closed invariant sets. And you can do the same thing with measures. You can find lots of fractal closed invariant or ergodic invariant measures. And if you don't like thinking about Hausdorff dimension of measures, then sorry, but I'm not going to define it. I'm not going to define Hausdorff dimension of sets, but An equivalent way of thinking about what Hausdorff dimension is in terms of metric entropy. So this is just saying that the metric entropy of the dynamics of F with respect to mu is, and because here my dynamics is affine, the derivative is constant, it's 3. So this is just log 3 times the dimension the Hausdorff dimension of the measure. So if you don't want to define, if you know what metric entropy is and you know what log 3 is, then you can define dimension, at least for this example. So for a single map with some hyperbolicity, there's a huge amount of fractal objects. There's fractal closed invariant sets, there's fractal measures. And that's just life, and you can cook these up very explicitly. There's a nice recipe for cooking up these. You can cook them up by symbolic dynamics, so they exist. And okay, so then what do I want to look at next is G from S1 to S1. G of X is 2X mod 1. And there's a few things to notice, which is that multiplication, 2 times 3 is the same as 3 times 2, I think. So remark is that G composed with F is F composed with G. They commute even mod Z. And log 2 and log 3 are irrationally related, I think. And that says that like G to the N equals F to the M. This happens if and only if N is equal to M is equal to 0. And so these things commute, but they commute in a non-trivial way. There's no power of one as a power of the other. And so this really gives us, it's not quite a group action, it's a semi-group action. We get a copy of the natural number squared. I don't know which continent I'm in. Does the natural numbers include 0 on this continent? Yes? Okay, so in France, the natural numbers include 0. So this is a semi-group, it has an identity. So this is acting on S1. And it's a higher rank semi-group acting. And so now the question is, so what are the joint invariant sets? And by set, I mean closed sets. And the same thing, what are the joint invariant measures? And I won't write down, but just maybe, to some extent, maybe you're more interested in the closed invariant sets than in measures. In this case, you could actually answer the question about closed invariant sets directly. But in other settings, sometimes in order to study closed invariant sets, you first study measures and then you say something about closed sets. Examples of closed sets are orbit closures. And so sometimes really what people are really interested in are orbit closures. If you want to study orbit closures, well, maybe you first study all the closed sets that are invariant. If you want to get to closed sets, maybe you have to start with measures depending on the setting you're looking in. Okay, I'm not supposed to do that. I'm breaking the rules already. Question, yes?
Do you have something related to the support of mu and omega?
Okay, so there I just said they exist. There are explicit constructions where you actually can build a lambda, and then you can take mu to be the measure of maximal entropy on that lambda. But there's lots and lots of constructions of those objects, so you can build the whole entire zoo of whatever you want. And so probably I should have written one more thing up there, but I'm not going to move it down, which is that somehow the principle behind any theorem that I write down or question that I write down today is that somehow a closed invariant set or an invariant measure for multiplication by 3 somehow sees triadic structures, and a closed invariant set for multiplication by 2 or an invariant measure for multiplication by 2 sees dyadic structures, and somehow dyadic and triadic structures are not supposed to talk to each other. So somehow, things mod 3 and things mod 2, they're supposed to not talk to each other because they're irrationally related. So here's theorem. of Furstenberg which is let lambda inside of S1 be closed and F and G invariant. So it's invariant under both maps, and it's a closed subset. So then so there are examples of these things. Either lambda is everything. I guess it could be nothing. Is nothing closed on this continent? I think so. Or there's another example, which is it could just be a collection of rational points, and if you take one rational point, take its orbit under the semi-group action, it closes, and so it could be a finite set of rational points, rationals, in parentheses, but it could be a finite orbit. So the answer of the closed invariant sets, you can completely classify them and really classify them. So then what's the question about measures? And so there's a lot of preliminary results about measures, and I'll just tell you what currently is the best result. So the conjecture, probably not a conjecture, question is, does the same thing hold for measures? So there's an obvious invariant measure, which is the Lebesgue measure or the Haar measure on the circle, and there's also Dirac masses sitting on the finite orbits. And is there anything else in between? And morally, yes, but technically we don't know. So here's the theorem, and this is due to Dan Rudolph. And it builds on work of Russ Lyons and Amy Johnson before. And it says the following. So let's let mu be ergodic. I'm going to put an asterisk here. F and G invariant. I'll stop writing the word Borel, but all of our measures are Borel measures. Probability measure on S1. So I'm going to put a period, and what do I mean by ergodic? So what does ergodic mean? So I don't mean that it's F ergodic or G ergodic. I mean it's ergodic as a semi-group action. So ergodic just means that the only F and G invariant sets are null or co-null. So it's ergodic as a group action or a semi-group action. So then let's see, what do I want to say? Okay, so there's an example, which is the Haar measure. How do I actually want to phrase the answer? Okay, so suppose that, no, I haven't decided how I want to phrase the theorem. So then okay, so there's no empty measures. So then either one, mu is the Lebesgue Haar measure on the circle, which corresponds to this conclusion, or two, we don't quite know how to say that has to be finitely supported, but we can say something that morally is the same thing, which is that the Hausdorff dimension of the measure has to be 0. So from some perspective, from a dimension perspective, it has to be very, very thin. And this is equivalent to simply saying that the metric entropy of F has to be 0, and the metric entropy of G has to be 0. And in fact, the metric entropy of anybody in the semi-group action has to be 0. So if you don't like dimension again, there's an entropy condition. And just to put it back into the language I have up there, one way that I think about this is I have, okay, it's not quite Z, it's N2, so it's not quite a group, it's a semi-group, but semi-direct producted with R. And so what is this? This is, and it's acting on the circle, N, M, and theta will be my parameter in R. This is acting by, so this guy, hit X is what, 2 to the M 3 to the n x plus theta mod 1. That's how, well, r acts on the circle by rotations, and then we have multiplication and by 2 and 3. And what are we assuming? We're assuming that mu is n squared invariant, right? Because it's invariant by f and g, and it's ergodic. And then under some mild hypothesis, which is the dimension being positive or the entropy being positive, so plus some entropy or dimension, is forcing it to actually be the Lebesgue measure. But what is the Lebesgue measure? It's the unique R invariant measure on the circle. So it's forcing it to be R invariant. So just putting back into the, my cartoon over there, somehow we started with n squared invariance, now we're getting R invariance. Okay. So I'm not going to quite prove Rudolph's theorem because, so Rudolph uses symbolic dynamics, and I probably understand enough of the symbolic dynamics to make up his proof, but I really like the smooth ergodic theory version of this. Unfortunately, n squared is not a group, it's a semi-group. You can turn it into a group action by going to what's called the natural extension, and the natural extension has non-Archimedean directions in it. It has a Q3 and a Q2 direction in it, and I don't know how to, well, I do know, but I don't want to think about non-Archimedean objects. So I'm gonna do a version, just replace this by a different cartoon, a different setup that morally has all the structures of Rudolph's theorem. But maybe before I do that, maybe I'll come over here, which is so, never mind. I'm gonna do what I'm gonna do. Okay, so here's the example that I'll work on for the rest of today and probably, I guess today, because I speak in the afternoon as well. Okay, so now I actually have to cheat and copy. So I can't help it, I wrote these matrices a long time ago, 3, 2, 1, 2, 2, 1. I checked that they have the properties I want them to have. And so as an exercise, you can do the linear algebra if you want. Okay, so here's 2 matrices that I made up. And here's a claim about various properties of them. So 1, they both have determinant 1. And they're defined, they have integer coordinates, and they have determinant 1, which means that they'll both induce automorphisms of the 3 torus. And because they induce automorphisms, then they define z actions, and so then I'll have a group action as opposed to a semi-group action. 2. Okay, I'm going to do it in the order that are in my notes. A has 3 real eigenvalues. And I still need to cheat. So chi A1 bigger than 1, bigger than chi A2, bigger than chi A3, bigger than 0. Am I going to use this whole board for linear algebra? I guess so. 3. B has the same thing. Has 3 real eigenvalues. They're distinct. Chi B1 bigger than chi B3, bigger than 1, bigger than chi B2. You might be very upset about why the superscripts are the way they are. So that's because I haven't told you bullet point 4, which is that A times B as matrices is B times A as matrices, so they commute. And so you know about commuting matrices that they're, if one is diagonalizable, they're jointly diagonalizable. So the ordering of the superscripts here is to indicate the joint eigenspaces of the 2 matrices. And 5, they don't commute for stupid reasons. So if I take A and a power of A, they commute. So A to the L b to the m is equal to, what do I want to say? Is equal to the identity if and only if L is equal to M is equal to probably 0. So neither is a power of the other, or even with inverses and things. So they really commute for a non-trivial reason. And so no, they can be negative, right? I also don't want B to be A inverse. So this is for all L and M in Z. So it's really a non-trivial reason that they commute. And so maybe just one remark about the linear algebra, since this tableau is about linear algebra, is that there are 3 joint eigenspaces, which I might as well call E superscript 1, E superscript 2, E superscript 3, and now the indexing on my eigenvalues corresponds to the corresponding index of the eigenspace. So both of these are diagonalizable, but there's a basis of eigenvectors, and the indexing is telling me which basis to work with. But then, more importantly, is that the A and B, they induce a z squared action on T3. And what is the action? I think I'm gonna call the action alpha, and I'll write a z squared thing as either a vector, or I'll write it as like a n comma m. And so alpha n comma m e an x plus a z3 is a to the n, b to the m, x plus z3. That's how it acts on a representative in the torus. And so we have a nice well-defined action here. Maybe none of the eigenvalues was 1 in modulus. I chose it so that they're all positive. None of them are 1 in modulus. So alpha of 1, 0, and alpha of 0 and 1. These are what are called the Nossoff. So they're very hyperbolic. There's as much hyperbolicity as you could want. We won't really use this, but. And maybe just one other remark is that alpha leaves no rational subtorus invariant. So there's no rational invariant objects. So somehow it should be irreducible, which you can already see. Whatever irreducible is supposed to mean, you can already see at the matrix level that as what do I want to say? The characteristic polynomials of these guys are irreducible over Q, which is the same thing as saying that there's no natural rational invariant objects here where your dynamics could be restricted to. Okay, so with my example, what do I want to say? So you can ask the same sort of questions for this kind of example. You could ask about what are the closed invariant sets, and you could ask about what are the joint invariant ergodic probability measures. And now I have to figure out how to swap the middle boards. So while I swap the middle boards, are there questions? So shortly after Rudolph proved his theorem, Anatole Katak and Ralph Spatzier tried to understand the proof, and maybe they didn't understand the proof, so they reformulated it a little bit differently. That included the setup that I have on the top board here. Okay, I don't know which buttons to push. It included non-Archimedean directions and included lots of other things. So here's just a very baby case of what they prove. So they prove a generalization of what Rudolph did. So here's a simple case of the Katak Spatzier extension of what Dan Rudolph did, which is the only alpha invariant, and let's say ergodic, alpha invariant probability measures on T3 are, well, there's the obvious one. There's the Lebesgue measure, or the Haar measure on T3. And there's some other ones, which is, again, you can take rational points, and you can look at you can put Dirac masses on a finite rational orbit. And again, we don't know how to reduce to that, but we can say, again, the dimension of mu is equal to 0. And this is equivalent to saying that the metric entropy of, and I didn't actually give notation, so let me say L sub A, and this will be alpha of 1, 0 is equal to 0, and that's the same thing as the metric entropy of L sub B, which is alpha of 0, 1. So again, those guys induce automorphisms of the torus, and you can look at the corresponding metric entropy of a automorphism invariant measure, and maybe they're very thin measures in the sense of entropy or in the sense of dimension. And again, you can ask the same sort of question about orbit closures, and you get the same corresponding theorem as Furstenberg, at least for this setting, because there's no rational invariant subtori. The orbit closures of the closed invariant sets are either everything or they're finite again. So I won't write that down, but you have the same sort of story for closed sets. So I'm going to focus on trying to outline a proof of this for probably most of my mini course. Is it clear what the theorem says? Maybe you don't know what Hausdorff dimension of a measure is, but.
Why did we skip the 2 torus?
Why do we skip the 2 torus? Because there's no higher rank abelian actions on the 2 torus. And the reason is that if I take T2, then sort of the automorphisms of T2 is, this is morally, and really up to finite index, it's SL2Z. And SL2Z doesn't have any higher rank abelian subgroups. And so you could study this. You could look at subgroups of SL2Z acting on the T2. And there's a very exciting story to look at there. But I picked something to do in 3 hours, and I'm going to look at abelian group actions. And there's just no abelian group actions to look at here. But if we look at T3, the automorphism group of T3, and again, it's up to whatever finite index, is basically SL3Z. And here, there's lots of abelian subgroups. For instance, the one generated by A and B live here. And so now I can look at measures invariant under a higher rank abelian subgroup. Is that an okay answer? Okay.
While you're erasing, is there some semigroup analog of times 2 times 3, maybe with the generators or something on the 2 torus that people care about?
Okay, so I almost said something along these lines. So since Katie's forcing me to, I will say something along these lines. Oh, that doesn't go any higher. Okay. If you do care about, if you want to study T2, or if you don't like abelian groups, one thing that you could study is instead of, so here, okay, I don't know what this arrow is for. So I'm going to focus on this group acting, Z, what is this called? Direct product, Z, is that what that's called? On some space. But you could instead look at Z semi-direct producted with, and I don't know if you can really make it semi-direct producted with Z, but you could like make it semi-direct producted with like a Q. Yeah, is there a Z semi-direct product Z inside of here? I don't think there is. But you could look at something like Z semi-direct producted with Q acting on some space. Or really, maybe, really the right way to think about it is R semi-direct producted with R. And what's an example of an R semi-direct producted with R? It's this group, e to the t, e to the minus t, s. It's upper triangular groups with determinant 1. That's the affine group of R, is R semi-direct producted with R. And so for instance, okay, so in this sort of story, you could look at some space where, for instance, you have an SL2R action happening on it. Maybe you know what like Teichmuller theory is and all these fancy words that I don't know. Okay, I should know them, but I pretend I don't. But that you could look at SL2R acting on some space, and then you could ask the question, you know, if I have mu is P invariant under solvable group that has some part acting very hyperbolically and some part that's acting sort of semi-direct, being normalized by the hyperbolic thing, you know, is mu SL2R invariant? And so this is another kind of question in this direction that you can ask. And it's sort of in this sort of stiffness kind of question. But if you have a group, you know, it's not quite abelian, but it also has some sort of, it's bigger than just a single copy of Z or a single copy of R. Is that an okay answer? And of course, you can look at the full SL2Z action on the torus and ask questions there. Okay, so coming back to sort of this prototype of a Katok-Spatzier type theorem or reformulation of Rudolph, let's just emphasize some structures that exist. Structures sort of in the T3 for the alpha action. And now I have to ask, when do I stop talking at 20? Okay. Somebody said I'm looking at Katie, but David's in charge.
You still stop talking at 20, no matter what.
So, okay, I'm just going to re-emphasize that there exists a Q, which is in where? Probably S, L, 3, probably this fancy Q, such that Q, A, Q inverse is chi A1, chi A2. So it doesn't really matter what order I put them in. Chi A3, Q, B, Q inverse, just because I said it out loud, but just to make it very explicit, they're jointly diagonalizable. So this is chi B1, chi B2, chi B3. So they're jointly diagonalizable and with the same index on the corresponding eigenspaces. E1, E2, E3, these are the joint eigenspaces. Yeah, probably you can't take it rational because they're irreducible over Q. Yeah, so probably Q adjoins some algebraic number. So let's just have it be R. Yeah, thanks. Sorry, I don't know why I wrote that. Yeah, you could do it in some sort of finite field extension, but. So, okay, everything here has been trivial except for my stupid mistakes. So Lyapunov functionals. So I'm going to have lambda superscript j. It's going to eat an element of Z2, and it's going to give me back a real number. In fact, it'll be log of an algebraic number. And what is it? Lambda j of n comma m. It's going to be log. And I haven't told you what base log is in, so you can pick whatever base you like, either 2 or e, whatever. log of chi a j, okay, to the n, and times chi b j to the m. And I ran out of room, but let me write this down. This is n log chi a j plus m log chi bj. And then the first thing to notice is that this is a morphism of Z2 into R, the way it's written. And so this induces a linear functional from Z2 sitting inside of R2 into R. And now I kind of have ran out of room, but I'm going to squeeze it here. I'm not going to squeeze it here. Let me actually use the boards the way they should be used. So, oh. This is the front. And then this is the second. Right, this chi j is an additive object, and then it extends uniquely. So I think of chi j really as a linear functional from r squared to r. This is linear, and then I restricted to Z2. So it extends to a unique linear functional. And then I also have, inside of T3, I will have what I'll call the Wj manifolds. So in various terminology, these would sometimes be called the Lyapunov manifolds. I'll tell you exactly what they are in a minute. Lyapunov manifolds. And so, okay, so what is this? So Wj parenthesis x. This is just x plus the corresponding eigenspace. And right, x lives in the torus, so R3 acts on the torus, so I know what this means. I know what it means to translate by somebody in here. So really this is the set of x plus v mod Z3, and so V is in the corresponding eigenspace. And there's these things exist for 1 less than j less than 3, the corresponding number of eigenvalues. And how does the dynamics work on these things? So here's, okay, the blackboard is the torus, I'm not going to draw it, but here's a point x, and here's the corresponding translate of the manifold, the eigenspace. So this is the Wj of x, and here's y. And if I apply my dynamics to it, so if I apply alpha of n comma m, I'm going to get some other point, which is alpha of n comma m of x. And I'll get another point, which is alpha n comma m of y. Because this is an eigenspace, they're still on the same manifold. So this is alpha of n comma m y. But now the distance may have changed. And how much does the distance change by? So if this distance is exactly L, then this distance, and you can just check this, right, just from the linear algebra, this is exactly e to the lambda j of n m times L. So distances along these manifolds, so the manifolds get permuted. This is not the same orbit as this one, but the distances get dilated exactly by what these functionals say they get dilated by. And one nice thing about working in, this is sort of the lowest combinatorics where you can do anything. You can work in higher dimensions. You can look at zk actions on TD. But a nice thing about working in this very low combinatorics is that for each 1 less than j less than 3, there is a pair n and m such that lambda j of nm is positive, and lambda k of nm is negative for k different from j. And so what does this say? This says that, so wj is the unstable manifold for the Anosov dynamics alpha of nm, because this is the only thing that gets expanded by the dynamics here. And well, the other two directions, they get contracted, and you could even say like ws, somehow because we're on the torus, everything's abelian, they jointly integrate. So somehow this is like I don't know what to write. wk1 sort of, okay, I don't know what I'm writing here, but the other two directions are stable, sort of is the stable manifold. But what's nice is that you can actually isolate each of these three directions as the unstable manifold for some element of the action. Everybody else is contracted. And okay, before I run out of time, I want to at least define the key object that we will study for the remainder. I think I'm going to take, which one is way back? That's 3. And you can't move 2 at once. Okay, so now I have mu, which will be a alpha, or Z2 invariant. I'll make sure that it's ergodic as a Z2 invariant object, ergodic measure on the 3 torus. And rather than studying this object on its own, I want to localize it. I want to induce. So I want to study okay, this is how mu looks along Wj, along these submanifolds. So these submanifolds, they form a foliation of my space. Maybe just a remark to say out loud, each of these leaves is dense of the Wj foliation. So to make whatever this quotation is supposed to say precise takes a little bit of work. So there's a few steps to do this. So first, pick a kasi sub j. I don't know, how do you pronounce this letter in Greek? I always called it kasi, because otherwise it sounds like psi or anyways. So you pick one of these objects. This is going to be a measurable partition subordinate to Wj. And I will define what it means to be subordinate to Wj. So this is, I'm not going to define what it means for a partition to be measurable. This is an uncountable partition, has uncountably many atoms. So the measurable is a really important assumption, but I won't actually say what that means. But what's important here is that Kasi j of x is contained in the J manifold through X. And that Kasi J, the boundary, if we take the union over all C in this object. So there's uncountably many atoms here, but if their boundaries have measure 0. And these things exist. You can build them by Markov partitions, for instance. If you know how to build Markov partitions for Nossoff diffeomorphisms, you can build an object exactly like this. You take the Markov partition and you restrict it to the unstable manifolds. Or you can build them sort of abstractly following Le Drapier-Streltson, if you know what that means. And so now I'm going to let mu, and I have to look at my notation, mu twiddle j of Cassie. This is the family of conditional measures associated to this measurable partition, at x. So what does this really mean? So I look at my manifold, and locally I've chopped it into local chunks of the Wj foliation. So here's a local piece of Wj of x. Here is x. And I'm drawing a cartoon in 2 dimensions, but it should be in 3 dimensions. And there is some mystery measure on here. And there's a general theory of conditional expectation, which then you can realize as conditional measures, which say that if I want to integrate a function on this rectangle, I can first integrate it with respect to some mystery measure on this leaf, and then I can integrate it with respect to some mystery measure on this leaf, and I can integrate it with respect to some mystery measure on this leaf, and then I can integrate it vertically. So I can do Fubini's theorem. I can disintegrate the measure, I can integrate horizontally with respect to some mystery measures, and then I can quotient out and I can integrate on what's left over. So there's a general theory which says that you have sort of on almost every leaf some sort of geometric object, some sort of conditional measure. So in pink is supposed to be the Cassie j of x. And of course it's sort of only defined up to a null set, so it's not maybe well defined on every leaf, but it's well defined on almost every leaf. And so this is what I mean by I want to study how mu looks like along these things, is I want to study these conditional measures. But there's a third axiom which I didn't write down. Well, it's sort of implicit in the fact that this is a measurable partition, which is that the atoms of this partition look like they're compact chunks. So Cassie j of x is compact. It's not quite what it means to be measurable, but it's morally what it means to be measurable, is compact in Wj of x. So here I've drawn it like it's coming from a Markov partition. There's more general constructions of these things, but the atoms of the partition are not dynamically equivariant. So here's maybe a problem with this construction, is that the atoms of the partition are not alpha equivariant, because, well, somehow the atom has a distinct size. It's not the full leaf. And so when I act on it by the dynamics, it gets contracted or expanded. And so these conditional measures, these are also not dynamically equivariant. And so I want to use the dynamics and I want to use the structure of these conditional measures to sort of study what this original measure was. And I have 11 minutes, which is, I think, I had enough time to actually actually make a point. So I'm going to rectify this problem, and then I'm going to try to tell you the strategy for how you actually go about doing this proof and any sort of measure rigidity proof that I know of. So if you don't know what a measurable partition is, if you haven't seen the theory of conditional measures, I apologize, but I'm happy to chat about that. And I have to figure out which board to use next. I think I'm on to the front board. Which one was back? This one. Okay, so I want to rectify the problem that these geometric objects that I actually want to study are not dynamically equivariant. There's a bunch of ways to overcome this. You can study them on their own and just keep track of the fact that they're not equivariant, but then that's a lot of bookkeeping. So let me replace it by something else. And these are often what are called leafwise measures. And so for x in T3, and again, this is only for mu almost every, we're going to build a measure, and here I'm going to call it nu sub x superscript j. Where's it going to live? It's not going to quite live on the leaf yet, on the leaf of the foliation. I'm going to build it on the corresponding eigenspace. And these are one-dimensional eigenspaces, so I'm going to think of this as a copy of R. I'm going to build a measure with what properties? So one, nu xj is going to be, unfortunately, it's not going to be a probability measure. It's not going to be a finite measure, but it'll be locally finite. So it's locally finite. Locally finite, parenthesis, but probably, and I'll tell you exactly when the probability hold, I can't abbreviate this, probably infinite. I'll tell you exactly when it's infinite this afternoon. Two, I'm going to have a map which goes from EJ, and I'm going to call it, I think I'm going to call it, I don't know if I'm going to call it phi or psi. I don't know what I'm going to use. I'm going to call it phi today. Phi j sub x goes from EJ to the corresponding leaf of the foliation at x. And what is the map? Psi j x of v is just x plus v. Right? To build this foliation, I stand at a point and I just translate by the corresponding eigenspace. And that's my canonical parameterization. And I can push forward these measures. So I'm kind of building two things at once. I'm building a measure on the eigenspace, and then I'm also building a measure on the leaf of the foliation. So if I push forward this measure associated to x, I'm going to get somebody else, and this guy I'm going to call mu sub x superscript j. And there's no assumption here. This is just a definition. But what do I want to say? Let's see. Nu is locally finite. I have this way of pushing it forward. And let me say a little bit more about locally finite. So I want to choose this guy to be canonically normalized. So this is locally finite. 3, nu xj is normalized on some I, which I will identify with -1 to 1 inside of the eigenspace. So I don't really care what identification I pick. Just pick some identification of your eigenspace with R and just normalize your measure. It's an infinite measure, but is locally finite, so have it take unit value on some fixed compact. So why not the unit ball? Okay, how do I know it's not 0? Is because the origin will always be in the support of these measures, just by how they're built. So I'm sweeping that under the rug, but the origin will always be in the support by how they're built.
What is the x plus wave in the circle? There is any structures on WB?
So x is in T3, which is R3 mod Z3, and V is in EJ, which is a subspace of R3. So now I know what it means to translate. So why do I want to have these two structures here? Is that if I look at nu j of x, and I look at nu j of y, where y is in the corresponding leaf of the foliation of x, So this is some sort of measure on the leaf of the foliation. This is also some sort of measure on the same leaf. So they should be the same, but they're not quite the same because I chose a different normalization. This guy is somehow normalized at an interval centered at x. This guy is normalized at an interval centered at y. So they're proportional. So this means that they agree up to a scalar constant. So i.e., so there exists a C which is positive such that the new j at x is a scalar multiple of the new j at y. So there is some sort of, they are somehow canonical, but they're not, the normalization isn't canonical. And 5 is that these things are dynamically equivariant. So alpha and m star of mu j at x should be related to mu j at alpha and m of x. So if I take the measure on the leaf at x, act by the dynamics, it should look like the measure at the corresponding leaf. But again, this is going to dilate the normalization interval, which means it has the wrong normalization. So again, they're only equal up to proportionality. So the fish, the alpha means proportional. And 6, so you can recover the conditional measures from the mu j x's as follows. So mu tilde j x is just my mu j x. So this is a finite measure on a compact chunk of the leaf. This is an infinite measure on the whole leaf. So I just restrict it to the corresponding atom of the partition, and then I just renormalize. Okay, so if you don't like conditional measures, and if you don't like how I'm extending them to leafwise measures, you can just assume all this structure exists and take this as for free. There's some work to actually build this. But this is the object I actually want to study. Question? Mm-hmm. Yes? Okay, so for mu almost every x, and technically if you want to be very precise, this is true for mu jx almost every y. So for almost every base point x, and then for the leafwise almost every, or the corresponding leafwise guy in the manifold, almost every point, there's a relation. Yeah, except that like the mu xj are really, really bad because they're infinite measures on a dense object. So there's no really good topology on it. But these guys have a nice topology. And so, yeah, the assignment x goes to nu xj is measurable. And that is important, and we'll use Luzin's theorem at some point on this family. The reason to introduce these guys is because it makes sense to make this sentence. It doesn't quite make sense to make that sentence about these objects unless you define a little bit more structure, like a compact open topology on measures or something. But so these guys, it's a measure from some space, 2 probability measures on the real line on how you're parameterizing. Okay, I have 1 minute. Okay. Am I allowed to take 2 minutes? But we have to be on time for lunch.
Yes, you get fewer questions after the end.
Okay, so what is the goal? We will assume that the metric entropy of somebody of alpha n m is positive for some n in m, for some element of the Z2. So this is what we'll assume at the beginning, and then we're going to show that these mu xj's, or the nu xj's, depending on how we're thinking about them, they are absolutely continuous with respect to the Haar measure on the Wj of x or R. And really, we'll focus on these guys. So I'll put these guys in parentheses. So we're going to show that these parametrized leafwise measures are absolutely continuous with respect to the Haar measure on R. And there's a few exercises here. This is going to imply that actually nu xj is equal up to normalization, so it's actually proportional to the Lebesgue measure on R. So this needs a little bit of a justification. And then this implies exercise, which will be an exercise, that mu is translation along the EJ eigenspace invariant. So we'll do some work to say that these mystery measures are actually absolutely continuous. They're in this measure class. There's a little bit of justification, which maybe I'll skip, but I'll tell you how to do it, that says that it's actually not just absolutely continuous, it's actually proportional to the Lebesgue measure. And once it's proportional to the Lebesgue measure, that gives you extra invariance of the measure you started with. So we started with Z2 invariance, and now we got Z2 semi-direct R invariance. So this is Z2 invariance plus entropy implies Z2 semi-direct R invariance, where this extra R is just this eigenspace direction. Okay, but these eigenspaces are defined over they're not rational. And so if we take a translation invariant measure on T3, what are the measures that are invariant under a very irrational translation on T3? It's just the Haar measure. So this implies that mu is the Haar / Lebesgue on T3. And so that's how you finish the proof, is by getting some regularity of these mystery leafwise measures. Once you get a little bit of regularity, then you can smooth it out and say it actually is the Lebesgue measure. Once it's the Lebesgue measure along these leaves, then it's actually, you get some extra invariance. From the extra invariance, you kind of can classify the measure. Okay, so I should stop because I took 4 minutes instead of 2.
I will allow a question of Aaron, and then we're going to go to lunch, and whoever asked the question should get this mic from me.
What's the general case of Katok-Spacich theorem? Just the same, but for n-dimensional tors?
So you can do it on tori. Oh yeah, I have the mic. So you can do it on tori. You can also do it on non-Archimedean tori, which are called solenoids. You can do it for zk on d-dimensional objects. But there are some technical hypotheses about the linear algebra of the matrices. Some of these were reduced by a follow-up paper by Einstein, Lindenstrauss. So you need some irreducibility, and you need what Katok-Spacich needed was non-proportional lambda j's. But you can overcome this with some diaphantiness. So there's not a good answer, but there's much more general things you can prove. David is a softie.
The matrix that commutes. You said that they commute for a non-trivial reason.
Yes?
But you didn't explain.
So, of course, A and A squared commute, and A inverse commute. But these matrices commute, but neither of them no power of A is equal to a power of B. And so that's the non-trivial reason, is that they don't form a Z action. They commute, if they live in the same Z orbit, of course they commute. But here they commute, when I'm saying non-trivial, I just mean that neither is a power of the other.
Basically, in this theory, non-trivial always means the group they generate isn't Z or virtually Z. With that, let's thank Aaron again so we can get lunch on time.